A piece of wire is bent in the shape of a parabola y equal to kx squared, y-axis vertical, with a bead of mass m on it. Bead is like a small object that can slide on the wire. Okay. The bead can slide on the wire without friction. It stays at the lowest point of the parabola when the wire is at rest. The wire is now accelerated parallel to the x-axis with a constant acceleration a. The distance of the new equilibrium position of the bead, where the bead can stay at rest with respect to the wire from the y-axis is. Okay, so there is a piece of wire bent in the form of a parabola y equal to kx square. Okay, recall functions even powers of x, so it must be symmetric about y-axis. Okay, so I'm going to show the parabola here. Okay, y-axis vertical. The bead can slide on the wire without friction. It stays at the lowest point of the parabola when the wire is at rest. So initially it is here. Initially the bead is here. It is now being accelerated parallel to x-axis with a constant acceleration a. So suppose this is the acceleration of the wire, ai cap. Okay. So obviously the bead is going to rise up and come somewhere here. Okay, because it slides on the wire without friction, there are only two forces that will act on the bead. First one is its weight. Okay, first one is its weight, it's downwards, mg, and the second force will be the normal reaction. Second force will be the normal reaction. Is that clear now? Yes. Okay, okay. Now, because they say that bead stays at rest with respect to wire, how does this interpret? Or rather, what does this interpret to? This means that acceleration of the bead is also the acceleration of the wire, right? Because it stays at rest with respect to wire. So in wire's frame of reference, it is stationary, right? Okay, so in our frame of reference, it must have a I cap as its acceleration. Okay, so again the problem is to resolve the normal component. Okay, the problem is again to resolve the normal component. Okay, so let us draw a horizontal line here. Okay, let me use a different color. Okay, let me draw this horizontal line, and I'm going to call the angle made by r with respect to horizontal as theta. Okay, I'm going to call this angle as theta. Can I say that r sin theta equals mg? Right, r sin theta equals mg because summation fy equals 0. The bead is accelerating in the x direction. Okay, so r cos theta will be m into a. That a is the acceleration of the bead. Okay, alright. Now, what do we want, by the way? What do we want? We want the distance of the new equilibrium position of the bead, where the bead can stay at rest with respect to wire from the y-axis. So we are looking for this distance. So essentially we are looking for the mod of the x coordinate, right? The distance of the new equilibrium position of the bead from y-axis. Okay, so we are basically looking for the mod of the x coordinate. Is that clear? So how to find it now? Look, does this not tell me tan theta? It does. Tan theta will be g upon a. Okay, tan theta will be g upon a, correct? Yes, tan theta will be g upon a. But is there any other way to find tan theta? What is tan theta? Look, tan theta is actually slope of normal. It is usually slope of derivative, a tangent. Okay, slope of normal. But in this case, because we have assumed that normal makes angle theta with horizontal, r is normal reaction. Okay, so this is g upon a. But we know from the theory of calculus that slope of tangent is dy by dx. Right? Slope of tangent is dy by dx. So y equal to kx squared gives dy by dx as 2kx. Okay, dy by dx as 2kx. So negative 1 upon dy by dx, which is slope of normal, will be negative 1 upon 2kx. Okay, so equate the two. Equate g by a with negative 1 upon 2kx. X, okay, will be negative a by 2gk, or mod x will be a by 2gk. A by 2gk, option B.